All right, this is Euclid Book 1, Proposition 2. To place at a given point, as an extremity, a straight line equal to a given straight line. So let A be the given point, so just give yourself a point, and that will be point A. And let BC be the given straight line. So give yourself a line segment BC, something like that. Now, it will be helpful to you here if you make sure the distance from A to B is not the same as the distance from B to C. That'll just make the drawing better later. And as you can see, my AB distance is smaller than my BC distance by quite a bit, so I'm good. All right. Thus, it is required to place at the point A, as an extremity, a straight line equal to the given straight line BC. From the point A to the point B, let the straight line AB be joined. So go ahead and join A and B with a line. That's pretty easy. There we go. And on it, let the equilateral triangle DAB be constructed, which we are allowed to do by Proposition 1. So on line AB, you want to build an equilateral triangle. So just a reminder, the way to do that is take a circle, centered at A with radius to B, and centered at B with radius to A. And where they cut each other on either side, call that D. I'm going to pick the left here. So I'm going to call that intersection right there D. And I'm going to join DA and DB. And I have made for myself a little equilateral triangle right there. There we go. All right. Let the straight lines AE and BF be produced in a straight line with DA and DB. So in a straight line, in other words, in a straight line with DA, I want to make straight line AE. So I want to extend DA out to some point E out here. So the way I'm going to do that here is I'm just going to draw a sort of infinitely long line from D to A, just to make sure I'm all lined up. There we go. And then somewhere out here, you want to make your point E. So I want to give myself lots of space, so I'll make it right there. You could, if you're drawing this by hand, just draw the line from A to E, as long as you're making sure it's in a line with D. There we go. And then similarly, we want to extend DB out to point F. So we want to extend DB out to point F. So again, I'm going to draw myself an infinitely long line from D to B. Yep, there we go. And call some point way out here F. Whoa, dear. Call some point way out here F. There we go. But again, you could just draw BF as long as you make sure it's in a line with D. There we go. All right, let's finish this. So with center B and distance BC, let the circle CGH be described. So we're going to draw a circle with center B and distance BC. So center to B with radius out to C. There we go. We want to draw a circle. That's circle CGH. G is actually going to be where that circle cuts BF. So here's BF. Where that cuts BF, that is going to be my point G. Yeah, my point G. That's right. That's right. There we go. And then H is just somewhere else in the circle, so I'll just put it right here for safekeeping. There we go. So this is now circle CGH. Okay. And again, with center D and distance DG, let the circle GKL be described. Oh, sorry, I need to burn my INJ first. There we go. So with center D and distance DG, let the circle GKL be described. So another circle, centered at D with radius out to G. So that's actually going to match the point we just had. There we go. All right. And that's going to be circle GKL. K, again, is just somewhere else on the circle. So I'll just put K right here. Why not? But L is going to be where AE was cut. So AE is cut at L right there. So there's my L. So there's my circle now, GKL. There we go. All right. And then that's sort of the end of the drawing. We're actually done now. Line AL is equal in length to BC. Maybe you can see that here. The line AL is equal in length to BC. But the proof of that is as follows. So since the point B, right here, is the center of circle CGH, which is the smaller circle, BC is equal to BG. In other words, since this line here and this line here are both radii of the smaller circle, these two lines are equal in length. That should make a whole lot of sense to you. Okay. Again, since the point D is the center of the circle GKL, DL is equal to DG. So since point D here is the center of this bigger circle, then DL and DG are equal in length since they are both radii of the same circle. Okay, the bigger circle. So they are also equal. Then Euclid says, and in these, DA is equal to DB. In other words, right here, our little equilateral triangle, right? Because the triangle is equilateral, this length is equal to this length. Okay, and so I think you can see where we're going here. This line equals this line. but this line equals this line, which means that this line must be equal to this line. Well, we know that this line equals this line, and so therefore this equals this. But you could go ahead and says it. So, and in these, dA is equal to dB. This line is equal to this line. Therefore, the remainder, AL, right here, is equal to the remainder BG. Okay, so I can just say it one more time. These are both radii of the same circle, so they're equal. These are equal, okay, because they're both they're part of an equilateral triangle, which means the remainders, this is equal to this, okay. So therefore, the remainder AL is equal to the remainder BG by common notion 3. But BC was already proved equal to BG because they're both radii of the smaller circle. Therefore, each of the straight lines AL and BC is equal to BG. So again, this line and this line is both equal to this line. And things which are equal to the same thing are also equal to one another. In other words, since AL equals BG and BC equals BG, then AL equals BC, which is what we wanted to do in the first place. So therefore, AL is equal to BC. Therefore, at the given point A, we have successfully made the straight line AL placed equal to the given straight line BC, which was the goal. Therefore, being what was required to do.